Welcome to the first video lecture really for Chemistry 315. Last time at the class meeting I showed some motivations for understanding thermodynamics and kinetics, physical chemistry generally. Now we're going to get into the actual details, and this lecture, despite the fact that it's very early and it's of course only a small part of the whole class, we'll cover some of probably the most important ideas that we will deal with in this class. So I hope everybody understands. If you have questions, I hope you ask them, and I hope these things are useful for the rest of the class. All right, so we're going to be dealing with cases where we have lots of atoms. And so on the microscopic scale, they're very complicated. If you have only a few atoms, then you can solve the classical equations of motion, for example. And what that will do is tell you all about exactly what each and every atom does. So if you've got an atom two atoms that are colliding, for example, solving the equations of motion will tell you exactly where each and every collision is happening. But if you've got 1,000 atoms, then this gets, of course, extremely complicated. And what's more, why do you want to know all those trajectories, right? Why do you want to know all that level of detail? You really don't want that. Furthermore, it gets increasingly hard to actually even do the solutions. And that's because of something called, well, chaos is the common word. Basically, something else that's called ergodicity, which is a way of saying that these trajectories get so complicated, something like over here, this picture, that you really can't even make any sense out of it in any way. Even if you could make sense out of it, it's not clear that it's the kind of thing you want to know. Everything gets crazy complicated and useless. So when you've got a lot of atoms present, and in fact most of the time we're going to be thinking about cases where you've got more than 1,000, where you've got millions or billions or Avogadro's number of atoms. What you want are statistics. You don't want the individual details. You want to know what large collections of atoms are doing all at once. And that is in fact going to be the main topic for at least the first half of this class, what are called equilibrium statistics. And after that we'll talk about kinetics. So the first half is thermodynamics and statistical mechanics. After that we'll talk about kinetics, but even in the kinetics section it's mostly going to be statistical behavior. It won't be quite so obvious, but it will mostly be statistical behavior that we are going to be worried about. So statistics and statistical behavior is really the only practical way to understand what's going on when you've got a huge number of molecules. What does that mean, and what are the principles behind it, and how can we get a handle on what statistical behavior is like as opposed to the details of solving the classical equations of motion, or maybe even the quantum mechanics of a bunch of particles. Let me say that while you can in principle do this kind of thing, it's also very difficult, of course, to even get solutions to cases like that. So, and it turns out that the statistics are often much easier to compute too. So, both for practical reasons and for a priori reasons, we want to do the statistics. All right, let's consider two cases over here on the right, on the left, that is, sorry. Case one, we consider just a bunch of molecules, little dots here, and they're all confined to one side of the box. Then we take out the barrier that's separating the two sides of the box, and we wait a while and we see what happens. Well, we know what's going to happen, right? The molecules are going to spread out. That seems like a really simple case. It's intuitive, at least to most of us, that that's exactly what's going to happen, but we want to understand why that happens. The answers are pretty simple, but very profound and have lots of implications. This particular case, in fact, is generalized appropriately, covers pretty much all the cases for all the behavior that we're going to talk about this semester. All right. The second case we want to talk about is a case where instead of having a bunch of atoms here and having those atoms spread out spatially, we're going to consider just one atom of hydrogen, one atom of chlorine, and those two atoms can in principle combine to form a single molecule of HCl. We know also that that will happen, right? That will take place, that reaction is very favorable, will take place spontaneously. But this looks at first glance like a totally different case than what's going on up above. Up above, there's no chemical reaction. Here we're going to form a chemical bond, right? So there are going to be mechanical forces involved in pulling these two atoms together. Up here, there are no mechanical forces involved. It looks like very different cases, in fact, but it turns out there's a deep level of commonality between these two. And if we understand both of these cases and understand how they're similar and how they're different, then we will cover most of the ideas, the most basic ideas that we'll need in this class. So here is me saying the same thing here in print. These two cases are basically all of thermodynamics. All the rest of the semester can be understood as a very detailed and long process of working out the details that are already implied by the answers to the two cases that we're looking at above. All right, let's look at case one first. We're going to assume something called the ergodic hypothesis. I already talked or used the word at least earlier. I used the word ergodicity. The ergodic hypothesis says that if you have a sufficiently complicated system, so probably more than about 100 atoms or somewhere in that range, probably 10 or 20 is even enough. 1,000 is certainly more than you need. Somewhere in the range between 10 and 1,000 atoms, you cross the threshold from non-ergodic behavior to ergodic behavior. What ergodic behavior means is that when you ask, for example, what are the positions and momenta, the kinetic energy, if you like, of all these atoms, well, every possible arrangement will be found, and every possible energy of individual atoms will be found so long as the total energy is conserved. And those will all be found with equal probability. That's what the ergodic hypothesis says. It isn't at all obvious at first that the ergodic hypothesis is true, but it turns out to be true, at least in the vast majority of cases. You can find exceptions to it, in fact. It isn't rigorously true, but right off the bat, off the top of my head right now, I couldn't even think of one, honestly. It's so universally true for at least a large enough number of atoms that it's universally assumed to be true. If that's true, then let's calculate how many states of the system, how many microstates of the system, that is, microscopic arrangements of these molecules, exist for this state. We'll call this a state of the system, everything confined to one half of the box. We'll call this a state of the system, everything allowed to run over the whole box. Let's calculate how many states exist for state 1 over here, and then again calculate how many exist for state 2. It turns out, and I will go through this in some detail if people are interested, that the number of states for this case, where the molecules are confined to a volume V1, is V1 to the nth power, where n is the number of molecules, divided by n factorial. So why is that, first of all, why does that sort of make sense? Well, if I choose just one of these molecules and I ask, how many places can this molecule, this one molecule be? Well, it can be anywhere in this half of the box, right? As long as it's not crossing through the barrier, it can be anywhere. And so there's V possibility, or V1 possibilities for that first molecule. Then for the second one, there's also V1 possibilities, right? And they're independent of each other. And so considering the two of them together, there's V1 times V1 possible ways to arrange both of those molecules at once. And then for the third one, there's V1 times V1 times V1, and so on. So you can see you're going to get this V1 to the nth power behavior when you're arranging a total of n molecules. Well, that's also true over on the other side. It's just that the volume is different. Here we have a total of V2. I mean, in this particular drawing, I've drawn things so that V1 is about half as big as V2. But it doesn't have to be that way. We can put this barrier, we can move this barrier around. Actually, I can do it like this. I can move this barrier around. And V1 or V2 can be as big or as small as I like. And these formulas are correct, no matter what those two V's are. Well, now I say, so this is counting how many microstates are available to the system depending on how much volume is available to the system. Let's take the ratio of those two. Which of those two is bigger? If the ratio is greater than 1, then W2 is bigger than W1. If the ratio is less than 1, then W2 is smaller than W1, so taking a ratio makes sense. If I do that, then there's the same number of molecules in both cases, so the n factorials divide out. And you just get that the ratio of the number of microstates available for those two cases is equal to the volume for V2 divided by the volume for V1 raised to the nth power. And if I then choose V2 to be twice as big as V1, like they're drawn up here, then that just becomes 2 to the nth power, right? V2 over V1 is 2, and so it becomes 2 to the nth power. Now let's look at what that ratio looks like when I choose n to be 1, 10, 100, or 1,000. In other words, as I start increasing the number of molecules that are in the system, if there's only one molecule, then the ratio of W2 over W1 is 2, right? There's only one molecule, and it has twice as much space to run around in when we have W2, when the barrier is gone. Then if the barrier is in place, that makes sense. Over here, I've taken the logarithm of this ratio. And the reason I do that is because it turns out that the logarithm of these things is closely related to the entropy. So we're starting to get to thermodynamics over here. We'll talk more about that in the next lecture. But I wanted people to look at the ratio anyway, even though we're not quite there yet. If I have 10 molecules, then the ratio is 2 to the 10th power, which is 1,024. That means that if we took a snapshot of this system up here, so we take the barrier out, the barrier was there, but we take the barrier out, what are the odds of just spontaneously, by chance, finding all 10 molecules over on one side, over on side 1 here? The answer is, well, if we take 1,000 snapshots, one of those is likely to show all the molecules on one side, just by chance, just by random chance. But the vast majority of the time now, 999 times out of 1,000, we're going to see something with a different ratio, where the atoms are more evenly spread out. They're not on just one side of the box. And that's kind of already happening when we've only got 10 atoms. Basically, we're seeing a statistical tendency for the molecules to want to be spread out on both sides, even when we've only got 10 atoms. If we go to 100 now, it's 2 to the 100th power. That's 10 to the 30th. That means we're never going to see anything except the atoms spread out. We're never going to see them all just on one side spontaneously. The statistics alone, there's no forces involved here. There's no energies or anything. There's no mechanical processes going on here, no mechanical forces. It's just statistics. It's pure statistics. And it's already determined that we're never going to see a state of the system where everything is just on half the box. If we go to 1,000 molecules, then it's 2 to the 1,000th power, and that's 10 to the 301 power, which is even more ridiculous. That just means, this one would mean you'd have to take 10 to the 30th snapshots before you even saw one case where everything was on one side of the box. And now you'd have to, down here, you'd have to take 10 to the 301 snapshots. Can't do that even in the age of the universe. I don't think you could even take 10 to the 30th snapshots in the age of the universe. So what does that mean? That means, let's see, that means that the statistics alone have, in a sense, locked what we'll see. What we'll see is always for the molecules to be spread out. And we can do a more complete calculation that asks how many are we likely to see on both sides, not just whether they're all on one side or not. And we'll see the same story. The distribution of probabilities is getting narrower and narrower just because of what's called the law of large numbers. And so what we will see macroscopically with, say, 100 atoms or few or more is that the atoms are always spread out, and that's just purely a result of statistics. All right, a few points. I said some of this stuff already. First of all, there are no forces involved. This is just a process of randomness along with random motion, right? Statistics combined with random motion. As long as the molecules aren't nailed down, as long as they're free to move around, and we calculate their statistics, their probabilities, then you'll get a result like this. Yeah, and it's a result of the statistics of large numbers. The statistics of large numbers and randomness together are enough to explain this macroscopic behavior. If this is a gas we're seeing here and we let this barrier out, macroscopically, we know the gas is going to rush to the other side. And the explanation for that is purely statistics. It has nothing to do with mechanical forces per se. And another way of saying that is that the statistics can cause motion. The fact that the gas rushes from one side to the other, what's the cause of that? Well, it's just a combination of randomness and statistics. It's not a mechanical force. And so statistics can act as an effective driving force. And we'll see this also more explicitly when I give a few examples further down. I didn't emphasize this earlier, but it's a really important topic that we'll talk about when we get into thermodynamics proper. All of this is sort of explaining what's going on at a basic idea sort of concept level, but we'll talk about the mathematics of thermodynamics next. And irreversibility is a big thing in thermodynamics. So here's our first example of that. This process is irreversible. Once these gas molecules are, as long as they're penned up, of course, they can't go to the other side, but once that barrier is gone, there's no way that they'll ever go back on their own. If you put the barrier over here and swept it, you could compress, of course, the molecules from the other side, but you got to do that from outside. Somebody from outside has to do that. The system itself will never return to its original state on its own. And, it's not strictly speaking true that it will never do it. It's just that the odds against it are 10 to the 300 power. And so it's irreversible in the sense that the odds against it are incredibly huge. And so that's what we mean by irreversible. Once things have spread out, they don't go back. This next point is a statement, almost, of the second law of thermodynamics, which is the core and center of thermodynamics. So after half a lecture on the first day of class, we've already reached the core of thermodynamics, and the reason for that is that thermodynamics at root, in its basic ideas, just isn't that hard. It just isn't that complicated. There's a lot of complicated outworkings of these ideas, but the core ideas are pretty simple. So here's what it is. Here's what it says, what point number 4 says. A change will occur spontaneously whenever the number of microstates in the final state of the system, so this is the full box, is much, much greater than the number of microstates in the initial state of the system. If the number of microstates gets bigger, if you've got a lot of molecules, it will get a lot bigger, almost always. Then the process will go on its own. It will go just because of randomness and statistics. And therefore, a spontaneous process, saying things the other way around, a spontaneous process will be one for which the number of microstates increases. Now, everybody here has had at least some exposure to thermodynamics before this. You should have little pings going off in your brain right now. This sounds like thermodynamics. This sounds like entropy. This sounds like the second law. It is the second law. Normally, though, that's stated by saying that a process will go spontaneously if the entropy increases. Here we're saying it'll go spontaneously if the number of microstates increases, and that suggests a very close relationship between entropy and the number of microstates, and that is in fact correct. There is a very close relationship. We'll talk about that. Actually, right down here, we'll talk about that in the next lecture. But to keep these lectures to a reasonable length, I'm going to stop here, and we'll talk about that next.